Okay, I'm gonna talk about some general epidemic modeling. I'm also going to talk about some things specifically related to the coronavirus epidemic. I want to start by acknowledging a group of us who've been working on this. This was organized by Michael Otterstader and Navid, who are BCCDC, and then there's people from SFU in Caroline Kalein's group, Mike Irvine, who's at BC Children's, my student, Rebecca Falcao, and Fred Brower, also in the math department, and Henry, who's at the BC Ministry of Health. I'm not going to be presenting specific results from our modeling project, but I'm going to be talking about general things, and I think this should be topical at any rate. Okay, so disclaimers. I'm not putting forward today too many original thoughts or results. This is really a synthetic talk I've put together. This is an update of a talk I gave in January, which was also sort of synthesized modeling from around the world. And this talk is like sushi in that it's probably okay today. If you leave it in the fridge, it might be okay tomorrow, but I really wouldn't touch it too much next week or the week after. This is a fast-moving thing, and so anything specific I say may or may not be relevant in the future. Okay, so coronaviruses. There's a nice picture of a virus there. There are already 4 circulating coronaviruses in the world. And in a test in 2018, about 12% of people who were in a particular study in the US who had influenza-like illness actually had a coronavirus. And out of 111 people in this study, there was 1 total day of hospitalization. So just because something's a coronavirus doesn't mean it's necessarily dangerous. On the other hand, there are 2 pretty well-known coronaviruses that are dangerous. The Middle East respiratory syndrome, which is sporadic in people who have contact with dromedary camels and occasionally leads to human-to-human transmission, has a case fatality rate, which is 30 or 40%, which is extremely high. And also we, in Canada particularly, remember SARS, where there was a large outbreak around the time I was moving to Canada in 2002, 2003. There were about 8,000 cases of the SARS epidemic. It had a roughly 10% case fatality rate. There were 250 cases in Canada and 43 deaths. So coronaviruses run the gamut. I would say the coronavirus we have today is less lethal and more transmissible than the SARS. I think everybody probably already knows that. Okay, so I want to talk a little bit historically about mathematical modeling efforts during the early phase of the epidemic, which was the first 2 months. So this is actually mostly slides from my talk at the end of January. So on the Thursday, January 30th, this map, whoops, what just happened? Okay, something bad just happened, and I lost my browser. Okay, hopefully everything's okay now. On Thursday, January 30th, this was a picture of the epidemic. There was a large amount of transmission. There were nearly 5,000 cases in Hubei province in China and spread around Southeast Asia and into North America. There were also a few cases in Europe by that point. And the early incidence data basically looked like this. The top left is sort of the first month. So from December 1st to January 2nd, entirely in Wuhan and Hubei, and then growing rapidly after that into January, and the graph in the bottom right, the histogram in the bottom right, goes up to the 23rd of January, and you can see the number of cases growing rapidly. I think I must have cut the image off there, but as you can imagine, it was ramping up pretty aggressively at that point. And then if we look overall in mainland China, you can see that during the period from January 16th till January 30th, represented on the left, we had a pretty good approximation of exponential growth. And in fact, on the top right, if you plot this out, then the cumulative number of cases over that time is showing a very good exponential growth during those first, during that 2 weeks in China, with a doubling time that was a little under 2 days. Okay. Internationally, we know that there was incidence was observed outside of China, that around the end of January, there were cases being reported outside, and there was person-to-person transmission in Germany, Japan, Taiwan, the USA, Thailand, And I just added here, even though it's not really in the first month, that in BC, the first person-to-person transmission was just in the beginning of March, not that long ago now. Okay, I include this slide really just as something you should do. So do yourself a favor and go to nextstrain.org and learn about the evolution of this virus. So this is a plot from nextstrain.org where a bunch of the strains are drawn out as a phylogenetic tree. So this is like a family tree, and it's rooted at the center. I chose to present it like this. And there's a wealth of data that you can explore and get sort of interesting insights into transmission in different countries and even different regions of different countries through the nextstrain.org website. I'm not going to talk any more really about evolution or phylogeny in this talk. All right, so that was the early phase. So now the phase from February 1st till now. Okay, so a number of things happened. The first thing is that while I was giving my talk on January 31st, we were very close, in fact, to the peak of coronavirus detection in China. And I think a lot of people would have heard yesterday that in China yesterday there wasn't a single confirmed case. Okay, so China was actually able to recover from a period of sustained epidemic growth of the coronavirus, and through fairly extreme social distancing was able to bring the virus under control and essentially get rid of the epidemic to the point where they should really be concerned about cases now spreading back into China from the rest of the world. Okay, there's also, I'll just highlight a few other epidemics. There was a major epidemic in South Korea. This was sort of interesting epidemiologically because a large part of the initial growth was due to 70 cases that were linked to a particular church service around mid-February. And I've indicated here to the right that now the Korean health authorities say that around half their epidemic can be linked back to that one spread at that church. So this is an interesting thing to see. There's been a major epidemic in Italy. On this one, I want to draw your attention to the onset of the lockdown. So the orange curve there is the total confirmed cases showing exponential growth. March. The onset of the lockdown in the north of Italy was around March 8th, and then it kind of became the whole of Italy in March 10th. And so how long ago was that? That was essentially coming towards 2 weeks ago. I think we should be following Italy very closely to see if there'll be a slowdown in the exponential rise of cases. There were hints of that actually a couple of days ago, and then unfortunately the second derivative became positive again, and the cases started to climb faster again, as it were. Okay, looking at the European epidemics, Simon Preston, who by the way was at UBC for a few months, he's now at University of Nottingham, he put together this nice graph a while ago, and he's showing essentially different European epidemics on the same axes with some time shifts. So the UK, for example, appears to be about 12 days behind Italy, which is furthest forward in its epidemic in Europe. And you can see here with the indicated line, there's about a 33% daily increase in a number of European countries, modulated by the time shift. This style of graph, this is from the Financial Times, with a lot more countries on it, and this is a little more up to date. And what you can see is a whole plethora of countries that are basically following that same slope line of a 33% daily increase, offset by time again. Some exceptions: Hong Kong, Singapore, Japan, South Korea. South Korea that we looked at before, but it's notable that South Korea certainly followed that initial trend for quite a long time before they came off of it. Okay. All right, in British Columbia, so this is data from yesterday. I actually just listened to Bonnie Henry on the radio on the way here, and there were 40 new cases today, so the number now is around 270. There was one additional death, so there have now been 8 deaths. You can see the geographical spread. It's primarily around Vancouver and the lower mainland. Okay, so what's the role of mathematical modeling? I'm going to summarize the epidemic up through now in different ways. what's the role of mathematical modeling in this? Well, we want to understand the rate of spread through populations. We want to be able to define, we want to find and define, estimate essential parameters about the spread. And ultimately, right now, we would like to predict what will happen. And you can imagine then different scenarios. So what happens if we do nothing? Or what happens if we have social distancing? What happens if we close the schools and so on? And I think it's very important to emphasize that we're doing this under considerable uncertainty, first of all, in the data. I think everybody's probably aware that the case counts that we get to work with are not necessarily what we would want for very understandable reasons in most cases, that they're just not up to date, or there are issues with how many cases are being counted. Are there asymptomatic cases that will never be detected? These kinds of questions. And also the models. I would say there are still, if you look around modelers around the world, you're going to find a lot of different kinds of models being used with different assumptions going into those models. Okay, so what's coming up in this talk? So first of all, I think it's my civic duty to talk about Rnaught and what Rnaught is and how people tried to estimate it, particularly in the early phase of the epidemic in Wuhan and in China. Okay, yeah, so stochastic models, which are appropriate when case numbers are small, and then also models for bigger epidemics. You could still use stochastic models, but in a lot of cases you can gain insights through differential equations. And you can do things like calculate the final size of an epidemic explicitly. You can model different public health interventions in these kinds of models. And then I'll wrap up. Okay, I wrote the word predictions there. I meant to take that out. I'll wrap up with thoughts and scenarios. Okay. All right. So Rnaught, the single most important epidemic parameter. Rnaught is the average number of new infections caused by a single newly infected person at the beginning of the epidemic. That's the naught. We're talking about in the beginning. And so often we'll have an Rnaught at the beginning of an epidemic when maybe there are no interventions, and then we may change that over into an R effective or just an R value later on in the epidemic when interventions are occurring. Okay, but at the beginning of the epidemic, Rnaught greater than 1 means that there's a chance of exponential growth. Okay, it's not guaranteed because a variety of random events could prevent the disease from reaching the exponential growth phase. On the other hand, if Rnaught is less than 1, then extinction is guaranteed. There's no way to win when you make a series of losing bets. Okay. So what are Rnaught values? Well, pandemic influenza, Rnaught was around 1.6. Polio, it's about 6. For SARS, it turned out to be about 2.5, most estimates. The measles, the Rnaught is shockingly high. It's about 18. That's why we have to vaccinate against measles. And also for whooping cough or pertussis. To find Rnaught empirically requires a lot of epidemiological work because you're tracing individual cases. And so it would be nice, and it is nice, that we can estimate Rnaught by using mathematical models of how the infection moves around. So a very simple way of doing this would be to say, okay, how many people do I contact per day? Well, that's C. What's the average probability of infection per contact? That's P. And what's the duration of time during which I'm going to be infectious? That's T. And if I multiply those three things together, then that should give me the average number of new cases that are caused by a single person. Okay, so to prevent an epidemic, we need to reduce one of those factors. So we either reduce the contact rate or the probability of infection per contact or the duration of infectiousness. And how much do we have to reduce? Well, we have to reduce things to the point where Rnaught is less than 1. Okay, so in the case of influenza, if you want to stop an influenza epidemic, you could potentially quarantine 37% of everybody who's susceptible to influenza. That might be something that you could consider doing on a short-term basis. In the case of measles, the Rnaught is 18, so you would have to reduce the contacts down by 94%. That's virtually impossible. So the only way that you can really reduce the Rnaught that much is by vaccinating a large number of people against measles. So that means the contact rate, which is between a susceptible person and an infectious person, is much less likely to be to occur, right? Because there's less susceptible people around because we vaccinated them all. Okay, this is called herd immunity. And so you can see that Rnaught tells us one thing, that Rnaught tells us, is how strong does the public health response have to be to prevent the epidemic from happening in the first place. And so this is sort of the theory of vaccination and herd immunity. Okay. All right, so then at the beginning of the epidemic, it's very important to estimate what the R0 might be to get a sense of how rapidly you expect the disease to spread through your population. Okay, so R0 is a number, and then you're asking for a, you're trying to get it from counts as a function of time. So the dimensions of those two things are different. So you're going to need a time to divide your R0 by. Okay, and we can use a model to try to parameterize that. Okay, so in the case of coronavirus, we could use, and this is what people did, was we can use the so-called SEIR model of infection. So the idea is that people start off as susceptible, and they become infected, and they move into the exposed class. And in the exposed class, they're not actually infectious to other people yet. Then after some period of time, they move into the infectious class, where they can infect other people. And then after some period of time, they're removed either by recovering and not being infectious anymore, or by potentially being quarantined or by dying. So this is the model drawn in boxes here. So we can say, well, maybe there's some rate sigma that you move from exposed to infected, and there's some rate alpha that you move from infected to recovered. Okay, and so if these are constant rates, then we can use some simple differential equation-based mathematics to calculate the transmission function, which I've plotted at the bottom, as a function of the amount of time that somebody's become infected. So I just used, I think, a rate of 1 over 6 per day, or an average duration of the exposed period of 6 days, and an average duration of the infected period also of 6 days, and I plotted this out. And you can see that the expected number of infections kind of climbs and then decreases as people leave the infected class in the end. Okay, and now I can also calculate then my R0. So my R0 is going to be some background transmissibility beta 0 times the integral of this function over all time. And you can do that integral, and it turns out to be your background transmissibility just divided by the length of the infectious period. So you can see here that the length of the exposed period doesn't really have any effect on the R0, and that's what you would expect. All right, so there's some actual math here, which is always, it's always a tricky thing to do on a slide. But if we just look at the data, so looking at the first line of the math here, just looking at the data here, you would say, well, looks like the number of infected people is climbing exponentially. So I write it as an exponential function. So that also means that the incidence, or the rate of change of the infected people, is also growing exponentially. So I can write that and differentiate, and I get another exponential function, just with a different constant in front of it. Okay, so what do I know? So I'm now looking at the third line of the math. All right, so the rate of newly infected people should be the integral of the transmission function times all the people that were infected an appropriate length of time ago. So here I'm doing a convolution of the transmission function with the rate of people entering the infected class tau time units ago, and integrating that over all time. Okay, now I can plug in my formula for the incidence. I'm now on the fourth line of the math, and then I do some simplification. I'm now on the fifth line of the math. And then I see on the right-hand side of line 5, I'm sure everyone's loving this part, that I have a Laplace transform. Okay, this is great. And it turns out, if I plug in my transmission function from the slide previously, that I can do this Laplace transform explicitly. Okay, and that allows me then to solve for my R0 in terms of little r, which is the growth rate that I observe in the incidence data, and two other parameters, which are the length of the exposed period and the length of the infectious period. Okay, that's fairly simple to do. So armed with that data and that method, two groups in China in the 3rd or 4th week of January did preliminary estimates of R0, and they found quite wide ranges between 2.3 on the low side and 5.4 on the higher side. Okay, and one of the groups also estimated the incubation period to be on the order of 5 days, which was in line with SARS. Okay, all right. Okay, so using mathematical theory, we can take epidemiological data and calculate the basic reproduction number for the epidemic. Okay, so what I want to move on to now is early time outbreak modeling using some kinds of stochastic models. And I want to start off with a very, very simple stochastic model that hopefully everybody can get behind. So this is just my model. This is not my model for coronavirus. This is just a model. So start with one infected person. And suppose that each infected person, basically, they roll a four-sided dice, and they either infect 0 people, or 1 person, or 2 people, or 3 people with equal probability. And then they never infect more than 3 people. Okay, so we can immediately say what the Rnaught is. The Rnaught is the average number of new infections produced by one infected person at the start of infection. I borrowed this slide. So the Rnaught is the average of 0, 1, 2, and 3, so that's 1.5. Okay, so we think the disease should spread. And I can simulate this process now. Okay, and I simulate it, and you can see starting from my 1 infected person, well, the first step, they infected 1 infected person. And then the next generation, it infected 4 people. But 2 of those didn't have any offspring, right? And so then I have the group on the left, there was 4 infections. The group on the right, there were 3, and so on and so forth. And it looks like the epidemic may well end up growing exponentially in this case. I can do this many, many times, okay? So I can do a whole bunch of epidemics, as many as I want, and then I can plot the number of infected people on the y-axis, and this is a log scale, so a straight line is exponential growth, against the generation number. Okay, and you can see the expected, you can see the growth you know, of many of my different simulations that I run. But what you don't see is that actually 41% of the epidemics that I had on the simulations page actually went extinct before anything really happened. Okay, so after 10 generations, for example, I have a whole bunch of, out of my 1,000 epidemics that I ran, I have, you know, over 400 of them have actually gone extinct. So even if a disease has an Rnaught which is greater than 1, you're not guaranteed to have exponential growth. There's still some probability of things going bad for the epidemic in the early days. Okay, so you can take these kinds of models and turn them around. Okay, so you can make a model which is just a little bit more complicated than what I just showed you, and you can run it many, many times, and then you can ask, for what parameters in that model do I get simulations that look like the data that's coming from the epidemic? Okay, so for example, 2 groups in China, the Imai et al. And Ryu et al. Generated, sorry, Imai's actually in London, my bad. They generated simulations using essentially estimates from SARS as a starting point, okay, for the generation time of the infection and the distribution of numbers of new infections. Okay, they included the possibility of people spreading to many, many individuals via wide distribution, and then running their simulation many times and comparing with the data allowed them to make some rather different estimates on what the Rnaught would be, somewhere between 1.5 and maybe 3.5. And a similar thing more recently has been done for the US. This is from the group of Ted Perkins. So what he did was he ran a fairly simplistic epidemic model, and he compared, well, his group compared, okay, so we're now looking at the graph in the bottom left, okay? The red is the data, and the black is the model, okay, for the number of symptomatic infections in the USA. And what you can see is that the number of, and there's 2 axes. The black on the left goes up to 1,000, and the red on the right goes up to 300. Okay, so what you see there, if you decipher it, is that the US was radically, the US testing rates were insufficient to pick up all the infections that were occurring in the USA, right? So assuming the model is correct, and the data, and then you can argue that the data is not correct. And on the right side, there's a similar thing, comparing reporting with the data and reporting in the model. Okay, the interesting thing about the model that I haven't shown is that it matches the deaths very well, and presumably the deaths were not underreported. Therefore, this gives them some additional confidence. And they're estimating that during late February, maybe the US was only detecting around 10% or less of community transmissions. Okay, so these are stochastic simulations being used to try to make inferences about the epidemic as it's running. This was an earlier model from Stochastic and various people in London. They used a stochastic SEIR, so susceptible, exposed, infected, recovered model with a time-varying infectivity. So people were more infectious and then became less infectious. And they fit it to Wuhan data and international locations early on. And they, again, found that the Rnaught was something like in the range of 1.6 to 2.9. Okay. Finally, I'm just going to mention some work which was done at SFU. So this is from the group of Caroline Colline, and this was an outcome from the hackathon that they had on coronavirus in February. So this is showing some input data to the model. So each line, each horizontal line on this is a history of one individual in Singapore during the Singapore outbreak. And you can, the purple is unexposed. The green is then the people who are infected but not yet symptomatic. Symptomatic is the darker blue color. Then green is hospitalized and yellow is discharged from the hospital. Okay, so they fit a stochastic, essentially SEIR model to this. And also data from Tianjin in China. And they found a significantly lower Rnaught than some people found, which was around 2. They also found, though, that the serial interval, i.e. the gap between infection and onward transmission, was probably faster than people had previously estimated, in the range of 4 to 5 days. And this is some evidence of pre-symptomatic transmission, which people have been talking about a lot. This figure I just showed here, they were in the lucky position of actually having epidemiologically traced outbreak clusters. So, you know, this guy here transmitted to this guy, and so on. Okay, I think here the direction of transmission is not clear, and that's why you get a non-tree shape there. Okay, and then I also want to mention, this is again from people in London. This is a more complex stochastic model. So in this model from Helliwell et al., we start off with person A in the top left. Interesting. We start off with person A in the top left, and they became infected, and then they have an incubation period, and then they start to show symptoms, and then you can see the event that they infect person B and person C. So this is quite a detailed level of simulation with assumed distributions on times of incubation, delays from symptomatic onset to isolation in a hospital or self-isolation, and explicit infection events. Okay, so this is, and this, so the reason that this is modeled carefully in this way with person A, person B, and person C instead of just with numbers is that quite often there is data of the form where contact tracing has happened, and so there are known transmissions, and this is trying to simulate the process of finding a particular person and then asking them who their contacts are. Okay, this is actually a little bit different than what was done in the previous stochastic models I was explaining, in that they're actually trying to simulate the process of epidemiological investigation as well as the epidemic itself. And this should, in principle, allow them to get a better fit to the data, because they're also modeling the measurement process as well as the process. Okay. So just some results from Helliwell, and I encourage you to take a look at this paper. It's a nice one. For 3 different reproductive numbers, so these would be background reproductive numbers, they switch on contact tracing as a percentage on the x-axis. So going from, so for example, if the Rnaught is 3.5, then as they switch on contact tracing in their model, they're able to reduce it down to below 1, only at about 100% contact tracing. On the other hand, if the reproductive number is down in between 1 and 1.5, then they're able to reduce it with relatively little contact tracing. Okay, this model wasn't exactly fit to data, but I think this is an interesting thing to do. I think this is an appropriate model for the BC situation that we're currently in. And what we're actually doing in our group is using an updated version of this model to include some other effects, such as import of cases and self-isolation as opposed to isolation following detection, to make projections about what the epidemic in BC is going to look like over the next few weeks. Okay, so stochastic models are really important for modeling the early stages of an outbreak or an epidemic, when the number of cases are small and you get essentially demographic stochasticity in different realizations of the process. And they can be used extremely easily these days for data fitting because we can simulate as much as we want and then only keep the simulations which fit the data, and then we can look at the parameters for those simulations and ascribe evidence that those parameters are right from the fit to the data. Once the epidemic reaches the exponential growth phase, though, so once you have hundreds of people infected in one place, then essentially you don't really need to do the stochastic strategy anymore, and you can move on to a differential equation models. Essentially, the central limit theorem tells you that everything is ultimately going to average out. And this is classic applied mathematics that we teach a lot to the undergrads. Now, the stochastic versions still work, but they're computationally more expensive. These days, that's maybe less of a barrier. Okay, so I want to talk now about the large epidemic modeling with differential equations. Okay, so I want to write down an explicit model here. So this is SEIR, the model I already talked about, susceptible, exposed, infectious, recovered, but written for large numbers of people instead of just for one person. So susceptibles are infected, and they're infected and become exposed at some rate that depends on, well, how many susceptibles there are, how many infecteds there are, maybe how many exposed, maybe it depends on time, these kinds of things. So the simplest version of this is just to have a parameter beta 0 in this case, and then it's basically, it's like physical chemistry. It's like a chemical reaction between two well-mixed species. Okay, so I guess you could say the population is well mixed in this case. So the susceptibles move to the exposed class at that rate. That's a nonlinear term. And then the exposed move on, as I said before, to the infected class at some rate sigma, and then they recover at some rate alpha and join a removed class. And the Rnaught for this model is exactly what I said before, which is beta 0 over alpha. So the transmissibility divided by the rate of recovery. Okay, and if you run this model, then you get a big scary prediction. Okay, so if we take Rnaught equals 2.5 and we have 4 million people, and so that would roughly speaking be British Columbia, and with an incubation period of 6 days and an infectious period of 6 days, and then an initial condition of 100 infectious people, then the peak number of infected people here is close to 500,000. I didn't put months on here, but if you want to say that day 0 is March 1st, then that's sometime in June. There would be 500,000 people infected in BC, and this would be completely overwhelming. So, however, that's not what's going to happen, but that is what the sort of well-mixed SIR model would say. Okay, and people did this. So Joseph Wu published one of the first sort of large-scale modeling papers back at the end of January, where he applied essentially this model with just a few tweaks to allow for mobility between different regions of China, okay, and included fitting data, getting an estimate for Rnaught, which was around 2.5. And so his graphs here for 2 different scenarios where they were reducing human mobility between different cities in China and also looking at the effects of reducing transmissibility. You can see even for his more optimistic scenario where transmissibility was being reduced, he was still having maybe incidences of 10 people per 1,000 population per day in the bottom right graph, and this is sustained for months. Okay, so there would be gigantic human cost if this model had come true. Now, of course, we know that this did not come true in China, and in fact, they were able to, keep people apart and prevent infection from happening so efficiently that the epidemic curve looked very, very different from Joe's paper. Okay, so one of the other things you can do, though, if you have this model, and there's a bit more math here, So you can take the model in the top left, and basically you can integrate it. So what we can do is we can add together the first three equations. So take ds dt plus dE dt plus di dt, and you see there's a lot of cancellation on the right-hand sides of the equations. So you end up with a relatively simple expression for the rate of change of s plus e plus I. Okay, so now we integrate that over all time, so over the course of the epidemic. Okay, and now working on the left side to begin with, those are all derivatives, so I can integrate them. So I get, that the n time value of susceptibles and the n time value of infected and exposed people minus the initial values. And most of those are 0 or close to it. I mean, the initial value of infected people is probably greater than 0, otherwise you don't get an epidemic, but it's close to 0. So basically you end up with the number of people infected at the end of the epidemic minus your total population size, which is n. Now working on the right side of the equality here, I can rewrite my my first equation in the differential equations and solve it for I, and I can see that I is equal to s prime over s with some constants, and so I can integrate s prime over s as well, and I get a logarithmic function, and then I can rearrange the whole thing, and I can end up with this transcendental equation, which tells me s infinity over n. And so that's the final size. That's the number of people, 1 minus that is the number of people who had the infection. Okay, so 1 minus s infinity over n is actually the fraction of the population who had the infection through the whole course of the epidemic. Okay, and so then you can solve that and you can plot that out. So here I'm plotting the final size on the y-axis as a percentage of the total population, and I'm plotting the Rnaught on the x-axis. And I'm highlighting here two values because the Public Health Agency of Canada has said, I think it was last week, they said between 30 and 70% of the population are likely to become infected with coronavirus. And so I thought, well, I'll just turn that around and say, okay, what does that mean they think the Rnaught's going to be? And so you can see the Rnaught is actually well below the values that were estimated from Wuhan or from Singapore. And that's because they believe, and I think they're correct, I hope they're correct, that there's going to be sufficient social distancing and quarantining that people are not going to spread the virus through the population as we might expect if we were fully well mixed. Okay. And just a note on this, it's much better to vaccinate your population to reduce the number of susceptible people than to let the epidemic run to reduce the number of susceptible people. There's a big difference between the number of people who will end up having had the infection versus the fraction that you would have needed to vaccinate to prevent the epidemic from happening in the first place. Okay, so this brings me on to three words that you hear a lot at the moment, and that is flatten the curve. So I'm plotting here just the simple SEIR prediction for different values of the Rnaught. Okay, and I kept the same parameters as on the previous plot. And so you can see in a sort of unmitigated epidemic with Rnaught of 2.5, there would be, hundreds of thousands of people infected at the same time. This would obviously be overwhelming for the healthcare anywhere. So flatten the curve is essentially, let's reduce Rnaught. So what we could do is we could try to reduce Rnaught maybe down to 2, and we still have hundreds of thousands of people infected at one time. We could reduce it down to 1.5, we can reduce it down to 1.2. And two things are happening here. First of all, you have less people infected all at the same time. And that's what people are mostly focused on in flatten the curve. But if I flip back to the final size calculation, then if I have my Rnaught down here at 1.2, then only maybe 30% of the population gets the infection. Whereas if it had remained higher, then almost everybody would have been infected by the end. Okay, so this is flatten the curve. The peak for Rnaught equals 1.2 is around 30,000 people infected at the same time. And so if 10% of all people need some kind of treatment in the hospital, this is about 75 per 100,000 of the population at one time. And that's not allowing for the fact that if you go in the hospital, you're probably going to be there for a week or two. This is very, very bad. The number of available ventilators, intensive care beds, and so on is well below that. Okay. There's another problem with flattening the curve, and I've tried to illustrate it here. So here, I modify the transmissibility of the disease as a function of time. So starting off with, at the beginning, we have 60 days of R0 equals 2.5. Then we have, okay, I want to say 100, I think it's 120 days of R equals 0.9. So remember, if R is less than 1, or R0 is less than 1, the disease can't even spread at all. So it shrinks. So the epidemic shrinks. Okay, that's fine. But then suppose that the measures are stopped and the R0 goes back to where it was. Well, then you end up with just about as big of an epidemic as you would have had in the first place if you hadn't done anything. So, the flattening the curve is fine, but you have to keep flattening the curve for a long time to have the effect. Okay, and people, just so you don't think SEIR is the whole thing, we can have quarantine. So here's the differential equations for a case with a quarantine class where exposed and infected people can move into the quarantine class at different rates, and then they can end up in the recovered class. And we can do this. And then you can extend further. You can include hospitalization and treatment and transmission within hospitals. You can have time-varying transmission parameters. One thing that I think is potentially interesting and important for the current epidemic is to have age-structured models with age-dependent mixing. So, you can have different age categories within each of the SEIRQ categories themselves. You can have variable activity levels. So some people have way more contacts than other people. You can build all this into different models. And I encourage you to have a look at the flu literature if you want to see people doing this as a serious business. And then immigration and emigration of cases as well. Okay. As you add this complexity to your model, then you're just throwing up problems of parameter estimation. Making sure that your numerical simulation is simulating what you think it is can also be an issue. With every extra piece of complexity you add to your model, you're forcing yourself to make decisions that you may not, to solve problems that may be difficult to answer, such as what is the transmissibility of this virus? What is the length of time that somebody spends in the exposed class, and so on. Okay, so that brings me on to almost my final sort of substantial thing. This is from the Imperial College team, the group of Neil Ferguson, and this was published a couple days ago. So this is the somewhat famous paper that Neil Ferguson was showing to people in Westminster in London, and it's supposed to have also heavily influenced policy decisions in the United States. So on Twitter yesterday, Neil Ferguson said that he thinks he has COVID-19, and I hope he gets better soon because he's been working very hard on this and doing a lot of good stuff. Okay, so I'm just going to basically present a few figures from that paper. I encourage you to go ahead and take a look at the Imperial paper. They just say it unvarnished. Given an estimated R0 of 2.4, they predict 81% of the British and American populations will be infected over the course of the epidemic. And so in figure A on the left there, you have the number of deaths per 100,000 population per day. Okay, and in Great Britain, this is 500,000 people would die in an unmitigated epidemic. They do say this is an unlikely course because the epidemic would be mitigated. People would not, I think, sit idly by if this was actually happening. In the US, there would be 2.2 million deaths in an unmitigated epidemic. This is just on the bottom right, just to point out that the age distribution of deaths would not probably be uniform. This is a report from the US CDC on outcomes among patients with coronavirus in the US. The light blue is hospitalizations divided by different age groups. ICU admissions is the medium blue, and deaths is the dark blue. And what you can basically see is there are very few deaths among children, and then it gradually grows, but there are certainly ICU admissions among all adult groups. So I think this is something we should all be aware of. Getting back to the Imperial College results. So here they're plotting critical care beds occupied per 100,000. And the red line at the bottom, the line that's not the x-axis, it's in red, is the number of critical care beds available in the UK on a per 100,000 basis. And you can see that even under a whole variety of proposed interventions, basically they're basically showing that R0 is greater than 1 for all of these, and that there would be that the healthcare system would likely be unable to respond. And this is the unfortunate situation in parts of Italy at the moment. Okay, they also proceed to show what will happen, and I showed this on a previous slide, if you switch off your efforts at some point, that basically everything just comes back. Okay, so then they're proposing a kind of a holiday sort of system where you impose social distancing and school closures for a period of time until things are looking okay, and then you let everybody go about their business again, hopefully with including some policies remain in force throughout, but you reopen the schools, and then you're able to keep them open. Then you close them when you start to see a signal that your healthcare system is about to become overwhelmed, and you repeat. Okay, so this is one run from their stochastic large-scale model, but a differential equation model would look very similar, showing that you'd have to keep the schools and universities closed for about 2/3 of the time in order for this policy to work out. So this paper, I think, was well done. It was timely for people in the West to hear this in London and Washington, and probably in Ottawa as well. So I'm happy that they did this work. Okay, so final thoughts. Okay, we're in uncharted territory for modeling an outbreak. We don't know. One of the issues we're finding with the modeling is trying to project what will happen when no one's done these things before. Okay, so we're trying to work from previous information from the SARS epidemic, from various studies that were done around influenza, looking at social distancing and school closures. There's also the current epidemic. We can look at the experience of China. We can look at the experience of South Korea. As I mentioned near the beginning of the talk, I'm very interested to see what happens in Italy over the next few days and weeks. Some interesting stuff to look at that I don't have time to talk about. Christoph Fraser in Oxford with, let's say, big data and tech people is looking at trying to do precision epidemiology, so precision contact tracing by installing apps on people's phones or having people install apps on their phones, which will then say, well, they test, and this is in conjunction with large-scale testing. You can say, well, Dan Coombs just tested positive. The 2 poor guys who were in the room with him for an hour had better get tested right away. So it's kind of precision contact tracing done on a large scale. So they're particularly interested also in the ethics of this. Improved treatment, I think, may be coming soon. There is a number of encouraging signs. There are a couple of links that I present, a couple of papers that I've linked there on malaria and antiviral drugs. A vaccine will presumably come along next year. And also summer is coming, and I wouldn't completely rule out a change in the transmission of this virus based on the seasons. With that said, it is pretty warm in Singapore, I think, a lot of the year, and they also had an epidemic, but we'll have to see. Okay, and I don't know how we're going to do questions, but thanks for sticking around, and I'm sorry about the technical difficulties at the beginning.
Okay, so let me grab a microphone. I know we're not all here in person, but we should somehow try to thank Dan for taking the time. So in your own way, if you could thank him in the usual way.
Thank you.
We do have some questions here on that. I have it here. So the first one here is we answered already. How did Health Canada arrive at their 30%, 70% population prediction? Is it possible?
Yeah, I'm going to go with a big I don't know on that one. But they have a way of doing this, and they have a large scale model, which is probably adapted from pandemic influenza modeling. So I would guess that would be where they came across this, and this would be assuming, obviously, changes, maybe not quite to the extent that we've now had changes, but that was a couple of weeks ago. So I don't know is the answer. Oh yeah, I'll repeat the question. Yeah, yeah. I'm gonna mute everybody again because I can hear some of these kids, which is great. But okay, yeah.
Is flattening the curve effective if it does not reduce the case load hospital capacity?
Yeah, because you end up with less cases. So maybe that wasn't totally clear, but if you flatten the curve, oh, sorry, is flattening the curve a good idea if you're still exceeding hospital capacity? The answer is yes, absolutely, because the peak is lower, which helps with many aspects of everyday life, but also the total number, the integral of that curve, the total number of people infected during the course of the epidemic also will be reduced. Assuming, of course, that you don't end up with another epidemic next year and another one the year after. But hopefully we'll have vaccination.
I've seen mention of latent immunity. Do you think this is a factor that's currently being overlooked?
So the question is about latent immunity, and I don't know what you mean by that. So I don't know.
This is from less serious coronaviruses.
Oh, ha. Well, you know, you got to wonder, right? You got to wonder. That's an interesting question. We've all been, well, many of us will have been exposed to other coronaviruses. Whether that is a good thing for our personal immunity or a bad thing is not clear. For example, there is in influenza the concept of antibody-dependent enhancement. So if you actually have antibodies to a related strain to the circulating strain, it can actually make, in mice, it can make the infection more severe. And, you know, there can be evidence, I'm struggling to think of it right now, but somewhere in my mind, there are examples of where certain age groups who may have been exposed, you know, so older people who are exposed to certain strains of flu may have a better or worse response. So yeah, immunological history could have an effect. Is it being overlooked? Well, it may be, but I'm not sure it's probably, if it's not something that's an obvious big deal, then maybe there are more pressing things to look at right now.
Yeah, the next question is how did SARS actually die down? There's never a vaccine.
I think SARS died down due to very good contact tracing. And although the Rnaught was estimated at 2.5, it presumably must have ended up being a bit lower than that once contact tracing was involved. I don't know a whole huge amount about the details of SARS, but I also have a bit of a feeling that maybe the world was a little bit lucky with SARS.
Yeah, there's a question about some people have many more contacts than others, so should we be targeting those people? I think they're trying to pick on politicians. Okay, so some people have more contacts than others. Should we be targeting those people? I don't like the word targeting. I think that everybody should make an effort to reduce their number of contacts over the next weeks. Yeah, some people have a lot of contacts for good reasons. Somebody's asking about spatial dependence and how it might play a role in modeling.
Okay, so the question is about spatial dependence in modeling. Right, so I would say probably explicitly spatial models are probably not terrifically helpful for this epidemic. However, metapopulation models, where we break up a larger population into smaller pieces and try to do epidemiological modeling within each piece, as well as allowing for connections between them, I think that's useful. So for example, in British Columbia, we have 5 or 6 health authorities. And we could imagine, you know, geographically breaking these up into different epidemics with, you know, a rate of movement of people between the different health authority regions. Although between Vancouver and Surrey, maybe not so much, but between Vancouver and Kamloops, this I think could be a useful thing in terms of predicting how big the caseload is going to be in different places.
Let me paraphrase. How much does does the modeling depend on the testing rate that affects the data?
Yeah, so somebody's asking, how much does the modeling depend on the testing rate, and how does this affect the data? This is a very big deal. The models are not going to be better than the available data. We can sort of agree on that. It's of concern that we're going to miss if the testing doesn't, for example, capture people who are asymptomatic and still infectious, or people who have mild symptoms and choose to self-isolate at home, versus people who actually end up being reported and tested. This makes it more difficult to model. Yeah, I mean, the ideal situation would be if everybody got tested every week, which is unlikely to happen, obviously. So one of the factors that we're forced to build into the models at this point is some kind of estimate of reporting. And there are different strategies for how you can build that in that I'd be happy to talk with people about offline. Yeah.
Are we expecting that China's going to do these holidays that Ferguson?
So the question is, are we expecting social distancing holidays as proposed by Ferguson in China? I have no idea. I really don't know what will happen in China. I mean, they didn't have any new cases either yesterday or the day before, so they're doing pretty well at this point. So if I was them, I would keep on doing some of what I was doing already.
A couple of people are asking about mutations.
Right. So the rate of mutation that's been detected. So I highly encourage you to go to NextStrainorg, which I highlighted earlier in the talk. It's a really nice resource. This outbreak has really highlighted the ability of labs to sequence and share the data about the genetic structure of the virus. The mutations that have been found, as you would predict, there are a few of them. There's not been enough large-scale transmission yet to see, large changes. The vast majority of mutations are going to be deleterious. So I wouldn't be expecting the virus to mutate to become more transmissible or anything like that anytime soon.
Just about out of the questions people have been asking, maybe I can just ask you can you finish on some kind of upbeat note, please?
Yeah, they beat this in China. They're in the process of beating us in South Korea. If we look back at that plot from the Financial Times, Hong Kong, Singapore, a large number of countries. I'm going to go back to the plot because I don't remember exactly who it was, but a large number of countries, have beaten or are in the process of beating this this infection. And I really believe that what we're doing in the province and in the country right now can be effective if it's done properly, if everybody does their bit. And I also have a lot of hope for antiviral treatment, which won't help with the hospitals being overloaded, but it will help outcomes of people who have the disease. And then I think a vaccine will come quickly, and let's all sort of cross our fingers for that. Anyway.
Okay. Well, with that, I think that's probably enough for taking up Dan's time. So let's thank him again in our own way, and I'm sure lots of people that are listening in know who he is and how to contact him, and we will continue to discuss this. So thanks again.
Great.
And bye for now.
Okay. Thanks.